Imagine that, for the first time in human history, you are sitting inside a spacecraft preparing to leave the solar system. The engines ignite. Earth disappears behind you. The moon becomes a small silver point. The sun shrinks into one more star among thousands. Ahead lies a destination that, from Earth, seems almost impossibly close, Proxima Centauri. It is the nearest known star to our solar system, roughly 4.24 light-years away. On a cosmic map, that distance is almost nothing. But, for a human civilization trapped beneath the laws of conventional propulsion, 4.24 light-years might as well be another universe. Imagine traveling at the speed of one of our fastest spacecraft. You would cross millions of kilometers, then millions more. The solar system would slowly disappear behind you. But Proxima Centauri would barely seem closer. Years would pass, decades, perhaps centuries. The stars around you would continue shining, as they always have, while your destination remained an almost unreachable point in the darkness. Now imagine something different. Your spacecraft begins accelerating. 10,000 kilometers per second, 50,000, 100,000. The stars begin to shift. At 200,000 kilometers per second, you are moving at roughly 2/3 the speed of light. At 250,000 kilometers per second, you are approaching a boundary that has governed every high-speed experiment humanity has ever performed. And then comes the number that has haunted every dream of interstellar travel. 299,792 kilometers per second. The speed of light in a vacuum. Approximately 300,000 kilometers every second. Fast enough to circle Earth more than 7 times in a single second. Fast enough to travel from Earth to the Moon in about 1.3 seconds. Fast enough to cross the entire Earth in a fraction of a second. And yet, on the scale of the universe, light is surprisingly slow. It takes about 8 minutes and 20 seconds to travel from the Sun to Earth. It takes more than 4 years to reach Proxima Centauri. About 26,000 years for light from the center of the Milky Way to reach us. And billions of years for light from some of the most distant galaxies we can observe to cross the expanding universe and arrive at our telescopes. The cosmos is enormous. Light is extraordinarily fast. But the universe is bigger still, and that creates a profound problem. If the speed of light is the ultimate speed limit, then interstellar civilization becomes incredibly difficult. Even traveling to nearby stars would require years. Traveling across the Milky Way would require tens of thousands of years. And reaching another galaxy could take millions or even billions of years. For an individual human being, these distances are effectively unreachable, so the question becomes unavoidable. Why can't we simply build a faster spacecraft? Why not develop a propulsion system powerful enough to push a ship beyond the speed of light? The answer begins with one of the most revolutionary discoveries in the history of physics. In 1905, Albert Einstein published his special theory of relativity. Among its many consequences was a radical conclusion. The speed of light is not simply another speed. It is built into the structure of space-time itself. For a particle with mass, increasing its velocity requires increasing its energy. At everyday speeds, the effect is almost invisible. A car can accelerate from 50 to 60 miles per hour without anything strange happening. A spacecraft can accelerate from 10 to 20 kilometers per second. The laws of motion remain familiar. But as velocity approaches the speed of light, the situation changes dramatically. Relativistic effects become increasingly important. The energy required to continue accelerating rises sharply. The closer a massive object gets to the speed of light, the more energy is required to increase its velocity by another fraction. At exactly the speed of light, the energy required for an object with non-zero rest mass would become effectively infinite within special relativity. And infinite energy is not an engineering challenge. It is not a matter of building a larger reactor. It is not a problem that can be solved by adding more fuel. It means that, according to our current understanding of physics, a massive spacecraft cannot simply accelerate through the speed of light. The barrier is fundamental. This is why the problem is so frustrating. Imagine possessing a spacecraft with engines far more powerful than anything humanity can currently construct. Imagine having an energy source capable of producing extraordinary amounts of power. You accelerate. The ship moves faster. The energy rises. You accelerate again. Faster still. But the closer you approach the speed of light, the more violently the energy requirement grows. 99% of light speed is possible in principle. 99.9% is possible in principle. 9,999% is still not forbidden for a massive object if enough energy and engineering capability exist. But crossing the final boundary is different. You can approach the speed of light indefinitely without reaching it. It is like climbing a mountain whose summit moves farther away every time you approach it. This is where many popular discussions about faster-than-light travel become misleading. The problem is not simply that we have not built a powerful enough engine. The problem is that the rules themselves appear to prevent ordinary matter from crossing the light speed barrier. But then something extraordinary happens. We look more closely at Einstein's own theory, and we discover that Einstein did not say that nothing in the universe can ever move faster than light in every conceivable sense. He said something more precise. No massive object can locally accelerate through space-time and overtake a light beam in its immediate surroundings. That distinction may sound like a technical detail. It is not. It may be the key to one of the strangest ideas ever proposed in theoretical physics. Because there is a difference between moving through space and changing space itself. Consider the universe on its largest scales. Space is not a rigid stage. It can expand. Galaxies are carried apart as the universe itself expands. And on cosmological scales, sufficiently distant galaxies can have recession velocities greater than the speed of light, without those galaxies locally breaking special relativity. They are not racing through their local space faster than light. The space between them is expanding. This reveals something profound. The geometry of space-time can behave in ways that ordinary objects cannot. And if space-time itself can expand, if it can contract, if gravity can curve it, then perhaps there is another possibility. What if a spacecraft did not need to travel through space at all? What if we could change the geometry of space around the spacecraft? Imagine the ship surrounded by a bubble. Inside the bubble, the spacecraft remains relatively at rest. It never locally exceeds the speed of light. Nothing inside the bubble needs to break Einstein's local speed limit. Instead, space itself is manipulated. Space in front of the spacecraft contracts. Space behind it expands. The bubble carries the spacecraft across the universe. From the perspective of distant observers, the bubble could potentially move at an effective speed far beyond what an ordinary spacecraft could achieve. The spacecraft itself would not be racing through space at faster than light velocity. Space would be doing the moving. This is the conceptual foundation behind what became known as the Alcubierre Warp Drive. And it came from an unexpected source, not science fiction, not a futuristic engineering laboratory, but from Einstein's own equations. In 1994, Mexican physicist Miguel Alcubierre proposed a mathematical space-time geometry in which a spacecraft could, in principle, be surrounded by a region of distorted space-time, a warp bubble. The idea was extraordinary. Instead of forcing a ship to accelerate through the universe, change the universe around the ship, it was as if nature itself could become the engine. The spacecraft would sit inside a region of comparatively flat space-time. Ahead, space would contract. Behind, space would expand. The bubble could move. And because the ship itself would remain locally within its own space-time region, the concept appeared to avoid the simplest form of the relativistic speed limit. But there was a problem, a very serious one. The mathematics allowed the geometry. It did not tell us how to build it. Alcubierre's original model appeared to require something exotic, regions of negative energy density, sometimes described loosely as exotic matter. No known spacecraft can manufacture such a substance in the quantities required. No known technology can shape space-time on the required scale. And the energy estimates associated with early warp drive concepts were so extreme that the proposal seemed to belong more naturally in science fiction than in an engineering textbook. For decades, the warp drive remained trapped in this strange middle ground. It was not simply nonsense. The mathematics came directly from general relativity, but neither was it a technology. It was a theoretical construction pointing toward a possibility that appeared physically unreachable. And yet, something important had changed. Humanity had discovered that the light-speed barrier might not be a wall surrounding the universe. It might be a wall surrounding the way we move through space. That distinction opens a completely different question. If matter cannot outrun light, could space-time itself be engineered to carry matter farther and faster? Could a warp bubble actually exist without the impossible ingredients demanded by the original proposal? And if so, how much energy would such a machine require? For decades, the answer seemed devastating. But then physicists began finding new mathematical pathways. They started asking whether warp geometry could be constructed with more ordinary forms of matter and energy. And that is where our journey takes its next step. Because the real story of the warp drive does not begin with a spacecraft breaking the speed of light. It begins with something far stranger, a spacecraft that never needs to. For more than a century, the speed of light has stood like an invisible wall around the universe. Nothing with mass can simply accelerate through it. No engine, no matter how powerful, can push an ordinary spacecraft from just below light speed to just above it. But there is a subtle distinction hidden inside Einstein's theory. A distinction so important that it would eventually inspire one of the most audacious ideas in theoretical physics. The question is not, how do we make the spacecraft move faster than light? The question is, what if we never make the spacecraft move faster at all? What if we move the space around it? To understand why this strange possibility exists, We have to return to Albert Einstein. Before Einstein, space was generally treated as a fixed stage. Objects moved through it. Planets followed their orbits. Stars traveled through the galaxy. Light crossed the vacuum. Space itself simply existed in the background, almost like an invisible theater surrounding everything else. Time was treated in much the same way. A second was a second. A clock on Earth and a clock somewhere else were assumed to share the same universal flow of time. Einstein changed that picture completely. In 1905, special relativity showed that measurements of space and time depend upon the motion of the observer. 10 years later, general relativity went even further. Einstein proposed that space and time were not separate entities at all. They were woven together into a four-dimensional structure called space-time, and space-time was not rigid. It could bend, it could stretch, it could compress, it could evolve. Matter and energy changed its geometry. The geometry, in turn, determined how matter and light moved. This was a profound departure from the old Newtonian universe. Imagine a rubber sheet stretched across an enormous frame. Place a heavy sphere in the center. The sheet bends downward. Roll a smaller ball nearby, and its trajectory changes because it is moving through that curved surface. The analogy is imperfect, but it provides an intuitive glimpse of Einstein's central insight. Gravity is not simply a mysterious force reaching across empty space. It is a consequence of curved space-time, and if space-time can curve, then perhaps it can be manipulated in other ways as well. It can expand, it can contract, it can change its geometry. We already know that the universe itself does this. Nearly a century ago, astronomers discovered that distant galaxies are moving away from one another as the universe expands. The galaxies are not necessarily racing through their local space at enormous speeds. Instead, the space between them is expanding. That distinction matters enormously because the universe has already demonstrated that space itself can change. The question is whether an advanced civilization could somehow control that geometry. Could we create a region of space-time that moves without requiring the spacecraft inside it to break the local speed of light limit? This is where Miguel Alcubierre enters the story. In 1994, Mexican theoretical physicist Miguel Alcubierre published a remarkable paper exploring precisely this possibility. He asked whether Einstein's general relativity could mathematically describe a spacecraft surrounded by a region of distorted spacetime, a structure that would later become known as a warp bubble. The idea was almost beautifully simple. Instead of accelerating the spacecraft through space, change the space around the spacecraft. Imagine the ship sitting inside a bubble. Inside that bubble, space-time could remain relatively flat. The spacecraft itself would not need to accelerate to extraordinary speeds. The crew would not necessarily experience the crushing acceleration that a conventional relativistic spacecraft would require. Instead, the geometry surrounding the bubble would do the work. Space in front of the bubble would contract. Space behind the bubble would expand. The bubble itself would effectively move through the universe. From the perspective of a distant observer, the spacecraft could potentially travel enormous distances in a very short period of time. And if the bubble were arranged correctly, its effective motion could exceed the speed of light. This sounds like a direct violation of Einstein. But here is the crucial point. The spacecraft itself does not locally move through space-time faster than light. Nothing inside the bubble needs to overtake a photon traveling alongside it. The trick is that the geometry of space-time itself is changing. This is why the concept is so fundamentally different from building a faster rocket. A conventional rocket attempts to increase its velocity through space. A warp drive attempts to alter the distance that space itself represents. The distinction may seem philosophical. It is actually mathematical. Consider a simple analogy. Imagine that you are standing inside a moving walkway at an airport. You are standing still relative to the walkway. Your feet are not moving across the floor under your own power, but the walkway carries you forward. Now imagine something far stranger. Instead of moving the walkway through a building, imagine the building itself changing shape. The floor contracts in front of you. The floor expands behind you. You remain in roughly the same local environment, while the geometry around you carries you toward your destination. This is only an analogy. Space-time is not a rubber sheet, but it captures the central idea. The spacecraft does not have to break the speed limit locally. The geometry does the moving. Alcubierre's mathematical solution was constructed specifically to exploit this possibility. A region of relatively flat space-time surrounds the spacecraft. Ahead of that region, space-time contracts. Behind it, space-time expands. The boundary between these regions forms the effective warp structure. If the bubble could somehow be controlled, the ship could be carried along with it. This produces one of the strangest results imaginable. From inside the spacecraft, the crew could remain almost stationary relative to their immediate surroundings. They would not simply feel themselves accelerating endlessly toward the speed of light. Instead, the distance to their destination would be altered by the geometry around them. The journey would be accomplished not by winning a race against light, but by changing the racetrack itself. And this is where the phrase "faster than light" becomes complicated. Suppose a warp bubble traveled from Earth to another star faster than a light beam would have crossed the same distance through ordinary flat space-time. An outside observer might describe the bubble as moving faster than light. But locally, inside the bubble, the spacecraft would not necessarily violate the speed limit imposed by special relativity. The ship's immediate motion through its local space-time could remain subliminal. No astronaut would simply press an accelerator and watch the speedometer climb beyond 299,792 kilometers per second. The apparent superluminal motion would come from the changing geometry of space-time. This is an important distinction. Warp drive is not a loophole in the sense of finding a technical error in Einstein's equations. It is better understood as an attempt to use the flexibility already contained within general relativity. Einstein's theory does not describe space-time as an immovable grid. It describes a dynamic geometry, and that geometry can produce effects that seem impossible from the perspective of ordinary Newtonian intuition. The Alcubierre metric takes this principle to an extreme. It asks what happens if we deliberately construct a particular geometry around a spacecraft. The resulting mathematical space-time possesses the characteristics required for a warp bubble. But there is a catch, a very large one. Einstein's equations do not simply give us the bubble for free. If the geometry exists, something must generate it. In general relativity, space-time curvature is related to the distribution of energy and momentum. In other words, if you want to bend space-time in a particular way, You need the appropriate physical source. And the original Alcubierre solution appeared to demand something extraordinarily difficult: negative energy density, a form of energy distribution unlike ordinary matter, something that no known spacecraft propulsion system can simply collect, store, and deploy. This problem would eventually become one of the greatest obstacles facing warp drive research. But before we reach that obstacle, it is worth pausing to appreciate what Alcubierre actually accomplished. He did not build a machine. He did not demonstrate that a spacecraft could fly faster than light. He did not prove that humanity could one day travel between galaxies in hours. What he demonstrated was something more subtle. He showed that the equations of general relativity contain a mathematical space-time geometry in which the distance between locations can effectively be manipulated in a way that permits apparent superluminal travel. That changed the question. Before Alcubierre, the conversation was largely, can anything move faster than light? After Alcubierre, another question became possible. Can space-time itself be engineered so that the destination comes to the spacecraft? That is a completely different problem, and it leads to an equally important realization. The spacecraft does not have to be the fastest object in the universe. The spacecraft may barely move at all relative to the space immediately surrounding it. Instead, imagine Earth and the destination star as 2 points drawn on a sheet of paper. Ordinary propulsion moves 1 point across the sheet. A warp drive attempts something radically different. It changes the sheet, compresses the distance ahead, expands the distance behind, and carries the spacecraft inside the resulting deformation. If such a geometry could be created and controlled, an enormous interstellar distance could potentially be crossed without requiring the spacecraft itself to achieve an ordinary velocity greater than light. This is why the Alcubierre concept fascinated physicists. It did not ask Einstein to surrender. It asked Einstein's equations to reveal what they were capable of. But the mathematics also exposed a disturbing reality. The universe may permit an exotic space-time geometry on paper, while making the physical ingredients needed to create it extraordinarily difficult or perhaps impossible to obtain. The original warp bubble required energy conditions that ordinary matter does not naturally satisfy. The amount and configuration of exotic energy appeared so extreme that the idea seemed to return immediately to the realm of science fiction. For decades, the warp drive remained trapped between two worlds, too mathematically serious to dismiss as fantasy, too physically demanding to be considered an engineering project. But that would not be the end of the story. Because once physicists began taking the equations seriously, they discovered something important. The original Alcubierre bubble was only one possible geometry. It was not necessarily the final answer. Researchers began asking whether the same basic concept could be redesigned. Could the bubble be shaped differently? Could its energy requirements be reduced? Could ordinary matter produce a useful warp geometry? Could a warp drive exist without the exotic negative energy that had made the original proposal seem impossible? These questions would eventually lead to a new generation of theoretical models, and they would force physicists to reconsider something they had assumed for decades. Maybe the problem was not the idea of manipulating space-time. Maybe the problem was the particular way we had first tried to do it. The universe had not necessarily closed the door. Perhaps We had simply been trying to open it with the wrong key, and the search for that key would lead directly into the most difficult part of the warp drive story. The energy problem. Imagine that you are sitting inside a spacecraft. The engines are silent. There is no violent acceleration. No enormous force pushes you against your seat. Your coffee remains in the cup. Your instruments remain stable. Your heartbeat is normal. And yet, outside the window, the universe appears to move. Stars that were millions of kilometers away seem to approach at extraordinary speed. The distance between you and your destination is shrinking. Behind you, the distance to Earth is expanding. The spacecraft itself appears almost motionless inside a small region of calm space. It sounds impossible. But this is the basic picture of a warp bubble. And understanding it requires us to abandon one of the simplest assumptions about space travel, that the spacecraft must be the thing doing the moving. For every spacecraft humanity has ever launched, the principle has been straightforward. The engines produce thrust. The spacecraft gains velocity. The spacecraft moves through space. The faster we want to travel, the more energy we must provide. A warp drive proposes something radically different. Instead of pushing the spacecraft faster through space, change the space around the spacecraft. That difference is the entire foundation of the warp bubble concept. Imagine a region of space-time surrounding a spacecraft. Inside that region is the ship and its crew. Around the outside is a distorted shell where space-time has a very different geometry. The interior can be designed to remain relatively flat. In this context, flat does not mean that gravity completely disappears. It means that the space-time immediately surrounding the spacecraft can remain comparatively undisturbed, while the strongest geometric deformation is concentrated around the bubble. This distinction is critical. The spacecraft is not supposed to sit inside a giant gravitational crusher. It is not falling toward a black hole. It is not being stretched by enormous tidal forces. Instead, the dramatic part of the geometry occurs around the bubble itself. Now imagine that the bubble has two sides. In front of the spacecraft, space-time contracts. Behind it, space-time expands. The spacecraft remains inside the relatively calm interior. The bubble, however, changes its position relative to distant observers. The result is something extraordinary. The spacecraft can effectively travel across a huge distance without behaving like a conventional high-speed vehicle. To understand why this matters, we need to distinguish between two concepts that sound similar but are fundamentally different: proper acceleration and coordinate velocity. Proper acceleration is closely related to what an observer actually feels. When a rocket launches from Earth, you feel yourself pushed into your seat. The engines are accelerating the spacecraft. Your body experiences that acceleration. That sensation is associated with proper acceleration. Now, imagine an astronaut floating freely in orbit. The spacecraft may be moving thousands of kilometers per hour relative to Earth, but the astronaut feels weightless. The spacecraft and astronaut are following the same path through curved space-time. Their relative motion is tiny, so enormous velocity does not automatically mean enormous felt acceleration. A warp bubble takes this distinction into a far more extreme theoretical regime. The spacecraft can remain approximately at rest relative to the local space-time inside the bubble. The bubble itself is what changes its position relative to distant regions of the universe. That means the crew does not necessarily need to experience the crushing acceleration that would accompany a conventional spacecraft trying to reach an enormous fraction of light speed. Imagine standing inside a moving room. You are standing still relative to the floor. The floor is carrying you forward. Now make the thought experiment even stranger. Imagine that the room is not moving through the building at all. Instead, the geometry of the building itself changes. The hallway ahead becomes shorter. The hallway behind becomes longer. The room remains locally calm, while the relationship between the room and distant locations changes. That is closer to the conceptual idea behind a warp bubble. Of course, real space-time is not a rubber sheet or a building. It is a four-dimensional geometric structure described by Einstein's equations. But the analogy helps reveal why a warp drive is not simply a faster rocket. Consider three different approaches to interstellar travel. The first is a conventional rocket. The spacecraft begins at Earth. Its engines burn fuel. Momentum increases. The spacecraft accelerates through ordinary space-time. When the engines stop, the craft continues moving according to its velocity. Every kilometer traveled is a kilometer the spacecraft must physically cross. The second approach is a relativistic rocket. The basic principle remains the same. The spacecraft itself moves through space, but now it approaches a substantial fraction of the speed of light. At 50% of light speed, relativistic effects become important. At 90%, they become dramatic. At 99%, the energy requirements become enormous. At 99.999%, the spacecraft is still below the speed of light. It can get extraordinarily close. But according to special relativity, it cannot cross the boundary. The third approach is the warp bubble. The spacecraft does not simply acquire a velocity greater than light. Instead, the geometry surrounding it is manipulated. Space ahead contracts. Space behind expands. The bubble carries the spacecraft. The crucial point is that the spacecraft's local motion through its surrounding space-time can remain below the local speed of light. The apparent superluminal journey comes from the geometry of space-time itself. This is why warp drive should not be described as an engine that simply makes a spaceship go faster. It is closer to a proposed space-time propulsion system. The engine would not primarily accelerate the ship. It would create and manipulate a particular geometry. And that creates a completely new engineering problem. A rocket engine has a relatively clear operating sequence. Ignite, accelerate, shut down, coast, then fire again when necessary. A warp bubble would be much more complicated. First, how would you create the bubble? Second, how would you make it move? Third, how would you change its velocity? And finally, how would you stop it? These questions may sound like engineering details. They are actually questions about the fundamental structure of space-time. To create a warp bubble, you need a particular distribution of energy and momentum. Einstein's field equations connect that distribution to the curvature of space-time. In simplified terms, matter and energy tell space-time how to curve. So if we want space-time to form a specific warp geometry, we need to produce the physical conditions capable of generating that geometry. And this is where the beautiful simplicity of the concept begins to disappear. Imagine designing a suspension bridge entirely inside a computer. The mathematical model can be perfect. You can calculate every beam, Every load, every stress, every vibration. You can simulate thousands of vehicles crossing it. But the simulation does not produce steel. It does not produce concrete. It does not build the bridge. A warp metric faces the same distinction. A mathematical solution can demonstrate that a particular geometry is permitted by Einstein's equations. But the equation does not automatically tell us how to manufacture the required energy distribution. It does not provide a reactor. It does not provide a control system. It does not provide materials. And it certainly does not provide a button labeled Engage Warp. The problem becomes even harder when we consider control. A warp bubble would have a specific shape. Its geometry would determine how space-time behaves around the spacecraft. Changing that shape could require changing the distribution of energy surrounding the bubble. Accelerating the bubble could require one configuration. Cruising could require another. Stopping could require yet another. Turning might require an even more complicated deformation. In other words, a practical warp drive would need something humanity has never learned to do. Reshape space-time deliberately and dynamically. We already manipulate electromagnetic fields. We can create powerful lasers. We can accelerate particles to nearly the speed of light. We can detect gravitational waves generated by black holes billions of light years away. But we have never created a macroscopic gravitational field on demand and shaped it into a controlled propulsion system. Gravity is extraordinarily difficult to engineer because the amount of energy associated with noticeable space-time curvature is immense. This is why there is such a huge difference between a theoretical warp drive and a real spacecraft. A mathematical model might tell us this geometry is possible within the equations. Engineering asks a much harder question. What physical system creates that geometry? And then comes the hardest question of all. Can we control it? That distinction matters because the original Alcubierre proposal did not solve these problems. It provided a mathematical space-time geometry. It did not provide a practical machine. The original model also appeared to require exotic negative energy densities, creating another enormous obstacle. For decades, that requirement made warp drive research look almost hopeless. But physicists continued exploring the equations. They began asking whether the Alcubierre geometry was the only possible way to create a warp effect. What if another geometry required less exotic energy? What if ordinary positive energy matter could produce a warp-like space-time? What if the bubble did not need to be exactly the shape Alcubierre originally proposed? Those questions changed the direction of the field. The goal was no longer simply to defend a science fiction dream. It became an attempt to map the entire space of possible warp geometries permitted by general relativity. And that search has produced an important realization. The original Alcubierre bubble may not be the final word. There may be other solutions. Some may be mathematically cleaner. Some may require less exotic energy. Some may obey more realistic physical conditions. But even the most promising equations still face the same enormous gap. A solution is not a machine. A space-time metric is not an engine. A computer simulation is not a spacecraft. And a theoretical possibility is not an experimental demonstration. That gap is where the real scientific story begins. Because if warp space-time can be redesigned, then perhaps the impossible energy requirements of the original proposal can also be redesigned. Perhaps we do not need the exotic fuel once thought unavoidable. Perhaps ordinary matter can participate in the construction of a warp geometry. And perhaps, for the first time, physicists can begin asking not whether warp drive mathematics exists, but whether some version of it could actually be produced by physical matter. That brings us to the next great obstacle, the substance that seemed to make warp drive impossible in the first place. Negative energy. For decades, it was the price of the warp bubble. And finding a way around that price would change the entire conversation. For a moment, imagine that humanity has solved the hardest part of the warp drive problem. The mathematics works. The bubble can form. The spacecraft can sit safely inside it. Space contracts ahead. Space expands behind. The destination begins to approach without the spacecraft ever needing to accelerate through the speed of light. It sounds like the breakthrough we have been waiting for. But then the engineers ask a very simple question. What powers it? And suddenly, the dream becomes much darker, because Einstein's equations do not allow us to bend space-time in arbitrary ways simply because we want to. The geometry of space-time is tied to energy and momentum. If you want to create a particular curvature, you need a particular physical source. And when Miguel Alcubierre first proposed his warp drive geometry in 1994, the required source had a remarkable property. It appeared to contain regions of negative energy density, not merely a large amount of energy. Not an exotic fuel in the science fiction sense. Something much stranger. Energy below the reference level, normally associated with empty space. To understand why this matters, we need to understand how Einstein's theory connects matter with geometry. General relativity is often summarized by a famous idea. Matter tells space-time how to curve, and curved space-time tells matter how to move. But the full relationship is more complicated. Einstein's field equations do not respond only to mass. They respond to the entire stress-energy tensor. Energy density, momentum, pressure, stress. All of these contribute to the geometry of space-time. A star curves space-time because it contains enormous amounts of mass energy. A black hole creates extreme curvature because its mass has collapsed into a very compact region. The Earth curves space-time far more gently. The equations determine what kinds of space-time geometries can be produced by different physical distributions of energy and momentum. And this is where physicists introduce a concept known as energy conditions. Energy conditions are mathematical constraints designed to capture certain intuitive ideas about physically reasonable matter. For example, one common condition, the weak energy condition, essentially requires that ordinary observers should measure a non-negative energy density. That sounds obvious. If you place a kilogram of matter on a scale, you expect the matter to possess positive energy. If you release a beam of light, it carries positive energy. If you convert mass into energy, the resulting radiation still carries positive energy. Ordinary physics overwhelmingly behaves this way. The null energy condition, or NEC, imposes another important constraint on how energy behaves along light-like trajectories. These conditions are not fundamental laws in exactly the same sense as Einstein's field equations. They are assumptions about what kinds of matter and energy distributions are physically reasonable, and many familiar forms of matter satisfy them. The original Alcubierre warp geometry does not. To produce the required space-time curvature, The model contains regions where the effective energy density becomes negative for certain observers. That was a devastating problem. Because if negative energy is required, where do we get it? The first instinct might be to think of antimatter. After all, antimatter sounds like the opposite of matter. Matter has positive mass. Perhaps antimatter has negative mass. Perhaps it could provide the missing negative energy. But this is not how antimatter works. Antimatter is not negative matter. An anti-electron or positron has the same mass as an electron. It has the opposite electric charge. An antiproton has the same mass as a proton, but the opposite charge and corresponding quantum numbers. When matter and antimatter meet, they can annihilate. Their rest mass is converted into other forms of energy, such as photons and other particles. But that does not mean antimatter possesses negative energy. In fact, antimatter contributes positive energy to the stress-energy tensor. A kilogram of antimatter does not weigh less because it is antimatter. It would gravitationally interact in the ordinary way expected for positive mass energy, Farnaz. So antimatter may be extraordinarily powerful as an energy source in principle, because matter-antimatter annihilation can convert a large fraction of rest mass into usable energy. But it is not the mysterious negative energy fuel required by the original warp drive concept. This distinction is essential. Antimatter is not negative energy. And this is where the story enters the strange territory of quantum physics. Because although negative energy seems impossible in ordinary classical physics, quantum theory allows something remarkably similar under certain conditions. Empty space is not truly empty. Quantum fields fill the universe. Even when no ordinary particles are present, those fields exhibit fluctuations and possess a vacuum state. Under special circumstances, quantum theory can produce regions where the energy density is lower than the energy density of a chosen reference vacuum state. One of the best-known examples is the Casimir effect. Imagine two conducting plates placed extremely close together in a vacuum. Quantum electromagnetic fields can occupy the space around and between the plates in different allowed modes. Because of the boundary conditions created by the plates, the spectrum of vacuum fluctuations between them differs from that outside. The result is a tiny measurable force pushing the plates together. The Casimir effect is real. It has been experimentally observed. And under an appropriate description, the energy density between the plates can be negative relative to the surrounding vacuum. For warp drive enthusiasts, this sounds enormously promising. Perhaps nature already provides negative energy. Perhaps we simply need to collect enough of it. Perhaps we could surround a spacecraft with enormous arrays of microscopic structures and somehow generate the negative energy required to create a warp bubble. But this is where the dream encounters another wall. The Casimir effect is extraordinarily small. The relevant quantum effects become significant only at extremely short distances. The amount of negative energy that can be produced is tiny compared with the energy scales involved in any macroscopic warp bubble. There is no known method for taking the effect between microscopic plates and scaling it up to something capable of reshaping space-time around a spacecraft. This is a critical distinction in theoretical physics. The existence of a phenomenon does not automatically mean that the phenomenon is technologically scalable. A laboratory laser proves that coherent light can be generated. It does not mean we can instantly build a laser powerful enough to move a planet. A nuclear reaction proves that enormous energy can be released from matter. It does not mean we can safely control stellar-scale energy. Likewise, a quantum effect producing a tiny negative energy density does not demonstrate that we can build a warp engine. The problem is not simply obtaining negative energy. It is obtaining the right amount in the right configuration for the right duration, while maintaining a stable space-time geometry. And those requirements are vastly more demanding. There is another complication. Quantum field theory places restrictions on negative energy. Negative energy cannot simply accumulate without limit. Quantum inequalities suggest that the magnitude and duration of negative energy configurations are constrained. The stronger the negative energy becomes, the shorter the period over which it can exist under many circumstances. Nature appears to permit small violations of ordinary energy conditions, but tightly restricts how large and long-lasting those violations can be. For a microscopic quantum system, these effects can be meaningful. For an interstellar spacecraft, they are nowhere near enough. This helps explain why the original Alcubierre concept quickly became associated with enormous energy requirements. Early analyses suggested that the amount of exotic energy could be absurdly large. Depending on the geometry, bubble dimensions, wall thickness, and assumptions used, estimates could reach astronomical scales. Some early popular descriptions compared the required negative energy with planetary or even larger mass energy scales. But these numbers should not be treated as one definitive fuel requirement. The estimates depend strongly on how the warp bubble is constructed. The important conclusion is more robust. The original geometry required an extraordinary stress-energy distribution, far beyond anything humanity can currently produce or control, that made the warp drive appear almost hopeless. The problem was not just that we lacked a sufficiently powerful engine. We did not possess the physical substance that the equations seemed to demand. And even if negative energy existed in the required quantities, another question remained. Could it actually be arranged into a stable warp bubble? The answer was unknown. This is why warp drive research remained largely theoretical for decades. The equations could be written. The space-time could be visualized. Computer simulations could display a bubble traveling across a virtual universe, but no laboratory could create the necessary geometry. No experiment had generated a macroscopic warp field. No spacecraft had been placed inside one. No known material could provide the required energy distribution. The gap between mathematics and engineering seemed enormous. Yet physicists did not simply abandon the problem. Instead, they began attacking the assumptions behind the original model. Perhaps negative energy was not fundamentally necessary. Perhaps the Alcubierre geometry was too restrictive. Perhaps a different warp metric could use positive energy instead. Perhaps the bubble did not need to travel at superluminal speed to demonstrate that the underlying concept was physically meaningful. These questions became increasingly important. A breakthrough did not require someone to suddenly invent a faster-than-light engine. It could begin with something much smaller. A mathematical solution satisfying more realistic physical conditions. A geometry that did not require negative energy. A model built from ordinary positive energy matter. That would not prove interstellar travel was possible. But it would change the question from, does this require impossible matter, 2. Can we find a physically reasonable space-time geometry? That distinction became the beginning of a new era in warp drive research. Researchers began exploring warp geometries that differed substantially from Alcubierre's original proposal. Some models investigated positive energy configurations. Others explored different bubble shapes, different velocity profiles, and different distributions of matter. The goal was no longer simply to make a theoretical spacecraft travel faster than light. The goal was to understand what kinds of warped space-time could actually be supported by known physical principles. And that shift is crucial, because science often progresses not by solving the original problem, but by discovering that the original problem was formulated too narrowly. The first warp drive asked, "How can we create this particular bubble?" The next generation asked, "What other bubbles does general relativity allow?" That opened a much larger mathematical landscape. And somewhere inside that landscape was a possibility that would have seemed almost unthinkable. In the early days of warp drive research, a warp geometry supported by ordinary positive energy matter, not negative energy, not antimatter, not mysterious exotic fuel, ordinary matter. It still would not mean that humanity had built a warp engine. It would not prove faster than light travel. It would not eliminate the enormous engineering problems surrounding space-time manipulation. But it would remove one of the most intimidating obstacles from the original concept. The impossible fuel might not be necessary after all. And suddenly, the questions surrounding warp drive began to change. It was no longer only a question of whether nature would allow the required energy. It became a question of whether we could learn to shape ordinary matter and energy into the geometry that space-time demands. That is a far more difficult engineering challenge, but unlike an engine requiring a substance we cannot produce, it is a problem that begins with something we already know exists: matter. And this is where the story of the warp drive takes its most important turn. Because decades after Alcubierre's original proposal, physicists began discovering mathematical ways to build warp-like geometries without relying on the impossible fuel that had haunted the concept from the beginning. For decades, the warp drive lived in an uncomfortable place. It was not quite science fiction. But it was not engineering either. The equations were real. The mathematics came from Einstein's general relativity. The space-time geometries could be written down. Computer simulations could make them visible. But whenever physicists asked the most important question, what physical substance could actually create such a geometry, the answer seemed to collapse back into the realm of the impossible. Negative energy, exotic matter, enormous energy requirements, unstable configurations, and a profound uncertainty about whether any of it could ever exist outside a mathematical model. Then, in 2021, a paper appeared that changed the way many researchers approached the problem. Its title was deliberately straightforward: Introducing Physical Warp Drives. The authors, Alexei Bobrik and Gianni Martire, were not claiming that humanity had discovered an engine capable of crossing the galaxy. They were doing something more fundamental. They were asking whether the concept of a warp drive could be placed inside a broader framework of physically meaningful space-time geometries. And their answer was surprisingly interesting. Perhaps a warp drive did not have to be imagined as an invisible bubble floating magically through space. Perhaps it could be understood as a physical shell of matter surrounding a region of space-time. That change in perspective may sound subtle. It was not. Because once you stop thinking of a warp drive as a mysterious engine and start thinking of it as a particular distribution of matter and energy, producing a particular geometry, you can begin asking the same questions physicists ask about any other physical system. What is it made of? How much energy does it contain? What stresses does it experience? Is it stable? Does it satisfy known energy conditions? What mass would an external observer measure? And most importantly, could the geometry exist using matter that actually obeys known physics? This was the conceptual shift. The warp drive became less like a magical spacecraft and more like a problem in gravitational physics. To understand the importance of the 2021 work, we need to go back to the original Alcubierre picture. The Alcubierre metric was designed to produce a warp bubble capable of apparent superluminal motion. But its energy requirements were deeply problematic. Certain observers would measure negative energy densities. That meant the stress-energy distribution supporting the geometry violated conditions that ordinary matter is expected to satisfy. The result was a beautiful mathematical construction, but a physically troubling one. Bobrick and Martyr approached the problem differently. Rather than treating the Alcubierre metric as the only possible warp drive solution, they developed a broader framework intended to encompass existing warp drive concepts while allowing other geometries. Their work demonstrated something important. Warp drives are not necessarily one single space-time configuration. There is a much larger family of possible geometries. Some can have properties that the original Alcubierre solution does not. And within that larger family, the researchers constructed examples of subluminal warp drives supported by positive energy. That phrase deserves careful attention. Positive energy and subluminal. Those two words are the key to understanding what this research did and what it did not do. It did not demonstrate a practical, faster-than-light spacecraft. It did not eliminate the speed of light limit. And it did not prove that an Alcubierre-style bubble can be constructed with ordinary technology. Instead, it showed that at least some warp-like space-time geometries can, in principle, be described using positive energy matter when the warp speed is below the speed of light. That may sound less spectacular than FTL. In reality, it is scientifically important because the question had changed. Previously, the warp drive discussion was dominated by, does this require impossible negative energy? Now researchers could ask, what physically reasonable space-time geometries can we construct? That is a much more productive question. Imagine that physicists are searching for a bridge across a canyon. The original Alcubierre design is like a bridge requiring a material that does not appear to exist. You can calculate every dimension. You can prove that the geometry would work. You can simulate thousands of vehicles crossing it. But the bridge cannot be built because the material itself is unavailable. The 2021 framework asks a different question. What if we redesign the bridge? What if we change the shape, change the support structure, change the loading conditions? Perhaps we can build a different bridge using materials that actually exist. The same philosophy applies to warp space-time. Instead of insisting on one particular metric, researchers can explore a family of possible geometries. And that family includes configurations with ordinary positive energy matter. This is why the 2021 paper was such an important conceptual development. The warp drive was no longer being treated simply as a single exotic solution. It became a broader class of possible space-time structures. But what exactly does positive energy mean here? In general relativity, the source of space-time curvature is not simply mass. The relevant quantity is the stress-energy tensor. It contains information about energy, density, momentum, pressure, and stresses. The geometry of space-time responds to all of them. That is why the energy conditions matter. The weak energy condition, for example, requires that observers moving along physically allowed time-like trajectories measure non-negative energy density. The null energy condition places restrictions on energy as measured along null directions. These conditions are useful because they encode broad assumptions about what physically reasonable matter should look like. But they are not magical laws that automatically prove a theory true or false. They are mathematical conditions imposed on the stress-energy distribution. And this is where the warp drive debate becomes surprisingly subtle. A model may satisfy one energy condition for a particular family of observers while violating another condition when the space-time is examined more generally. That distinction became especially important because other researchers quickly challenged optimistic interpretations of positive energy warp models. In 2021, Jessica Santiago, Sebastian Schuster, and Matt Visser argued that generic physically reasonable warp drives still face unavoidable violations of the null energy condition and therefore related energy conditions within standard general relativity. This disagreement is not a minor technical footnote. It demonstrates exactly why theoretical physics requires careful interpretation. One paper can find a mathematically promising configuration. Another can examine the same class of geometries from a different perspective and identify a deeper constraint. That does not mean the research is useless, quite the opposite. This is how theoretical physics works. A proposed solution is tested. Its assumptions are challenged. Its mathematical structure is examined from different angles. Weaknesses are identified. The model is refined. And gradually, researchers discover which possibilities survive. There is another concept that becomes particularly important here. ADM mass. The acronym comes from Arnowit, Deser, and Misner. In simplified terms, ADM mass is a way of characterizing the total mass energy associated with an isolated gravitational system as viewed from far away. It is not simply the amount of ordinary matter you could place on a scale. In general relativity, gravitational binding energy and the geometry of space-time itself matter. The total gravitational system has to be described globally. For a physical warp drive model, ADM mass becomes important because it tells us something about the overall mass energy budget of the space-time configuration. And this leads to a crucial insight. A warp drive cannot simply be treated as a bubble that magically moves through empty space. It has a physical gravitational source. If the geometry is supported by a shell of matter, that shell contributes to the system's total energy and mass. The warp drive, therefore, has to obey the bookkeeping rules of general relativity. Energy cannot simply appear because the geometry looks elegant. The space-time has to be supported by something. This is precisely what makes the 2021 framework conceptually powerful. Bobrick and Martyr argued that a warp drive can be understood as a shell of regular or exotic material moving inertially with a certain velocity. They also emphasized a point that is often lost in popular discussions. A warp drive still requires propulsion. In other words, the warp bubble is not a free ride. The geometry does not magically propel itself. Some physical mechanism must establish and maintain the configuration. The phrase warp drive can therefore be misleading if it creates the impression of a bubble that simply appears and carries a spacecraft wherever it wants to go. Physics does not give us that shortcut. Even a theoretically acceptable warp geometry must have a physical source. And here we reach an important distinction. A positive energy warp drive is not automatically an FTL warp drive. This distinction should never be lost. Imagine a spacecraft traveling at 90% of the speed of light inside a theoretical positive energy warp configuration. That would already be remarkable, but it would still be subliminal. It would not violate the local light speed limit. It would not demonstrate faster than light communication. It would not allow a spacecraft to cross the galaxy in an instant. And it would not solve the fundamental causal problems associated with superluminal motion. The 2021 framework explored positive energy subliminal solutions precisely because they are a more physically conservative starting point. It is easier to ask, can we construct a physically reasonable warp geometry that moves below light speed than to immediately demand? Can we construct a stable positive energy bubble that travels faster than light? The first question gives physicists something concrete to analyze. The second introduces much deeper problems involving horizons, causality, energy conditions, and quantum effects. In fact, the same 2021 paper explored superluminal warp drive solutions, satisfying certain quantum inequalities, but that should not be interpreted as demonstrating an experimentally realizable FTL machine. This is where scientific language matters. Mathematically permitted under a model is not the same as physically demonstrated, and physically possible in principle is not the same as technologically achievable. There are enormous distances between those statements. So, why does the 2021 work matter so much? Because it changed the architecture of the problem. Before, the warp drive was often discussed as a single extraordinary idea, the Alcubierre bubble. Afterward, researchers could think in terms of a broader landscape: warp drive spacetimes, different geometries, different energy distributions, different velocities, different stability properties, different physical assumptions. That is a major conceptual improvement. It means the original Alcubierre metric is not necessarily the final destination. It may simply be the first famous point on a much larger map, and that map can now be explored. Researchers can ask, what happens if the bubble is thicker? What happens if the energy is distributed differently? What happens if the velocity is lower? What happens if the matter shell has a different pressure profile? What happens to the energy conditions? What happens to the ADM mass? What happens to the stability of the geometry? What happens when the bubble interacts with ordinary matter? These are physics questions, not science fiction questions. But there is still an enormous problem. Even if a mathematical solution satisfies favorable energy conditions, where do we get the matter? Where does the energy come from? How do we assemble the shell? How do we create the required space-time curvature? How do we stabilize it? How do we control it? How do we accelerate it? How do we stop it? And how do we prevent the entire configuration from becoming unstable? Nothing in the 2021 framework solves these engineering challenges. The researchers themselves did not claim to have built a propulsion system. Their contribution was theoretical. They showed that certain classes of warp geometries can, at least in principle, be constructed within known classical physical principles. That is very different from building a spacecraft. But science often advances through exactly this kind of distinction. First, a phenomenon is mathematically imaginable. Then, researchers determine whether the mathematics is internally consistent. Then they ask whether the required physical conditions exist. Then whether those conditions can be produced. Then whether they can be controlled. Then whether an experiment can detect the effect. Only after all of those steps does technology begin to emerge. Warp drive research is still somewhere near the early stages of that ladder. We have mathematical geometries. We have competing analyses. We have theoretical models. We have simulations. But we do not have a laboratory warp bubble carrying matter across a room. We do not have a warp engine. And we certainly do not have a faster-than-light spacecraft. Yet something important has changed. The question is no longer as simple as, is warp drive nonsense? The mathematics has made that question too crude. The better question is, which warp geometries are compatible with known physics, and what physical resources would be required to create them? That question is harder, but it is also scientific. And once researchers began asking it, another possibility emerged. Maybe the original Alcubierre bubble demanded too much. Maybe its negative energy requirement was partly a consequence of the specific geometry chosen. Maybe space-time could be warped using a different configuration. Maybe ordinary matter could do some of the work. And if that were true, the dream would still be extraordinarily far from a practical spacecraft. But one of its most intimidating walls would have moved. The impossible fuel would no longer be the only story. Now the challenge becomes something even more concrete. Can we design a warp geometry that nature will actually support? And that question would soon lead to another important development. Because researchers did not stop at the 2021 framework. They began looking for increasingly specific physical warp configurations. Configurations with ordinary matter. Configurations with controlled velocity. Configurations that could be described not merely as elegant mathematical bubbles, but as possible physical systems. And that is where the next chapter of the story begins. Not with faster-than-light travel, not with a starship, but with a much smaller and much more important step. A warp drive that can exist without the impossible fuel. For 30 years, the warp drive idea remained trapped between mathematics and reality. The original Alcubierre metric had shown that general relativity could describe a space-time geometry resembling a warp bubble. Later researchers found ways to reduce some of its most extreme energy requirements. And by 2021, theoretical physicists had begun constructing models of positive energy, subluminal warp drives. But there was still a fundamental problem. The equations were becoming more interesting. While the spacecraft remained completely imaginary, then something changed, not in a laboratory, not in a launch facility, but inside the mathematics. In 2024, Jared Fuchs, Christopher Helmerich, Alexei Bobrik, Luke Sellers, Brandon Melcher, and Gianni Martire published a paper with a deliberately unglamorous title, Constant Velocity Physical Warp Drive Solution. The title itself tells us something important. This was not a paper announcing faster-than-light travel. It was not a claim that a warp engine had been built. And it was not a demonstration that humanity could cross the galaxy in minutes. Instead, the researchers presented a constant velocity, subluminal warp drive solution designed to satisfy the known energy conditions. At first glance, that may sound like a disappointment. After all, the dream is faster than light. But the significance lies somewhere else. The researchers were trying to answer a much more fundamental question. Can a warp drive geometry be supported by ordinary positive energy matter without requiring the exotic negative energy that haunted the original Alcubierre proposal? Their mathematical construction provided a striking answer. Under the assumptions of their model, yes. To understand what changed, imagine going back to the original warp bubble. Alcubierre's geometry can be pictured as a region of space-time surrounding a spacecraft. The space ahead contracts, the space behind expands. But the energy distribution needed to produce that geometry creates serious problems. Negative energy appears. Energy conditions are violated. The physical source is unclear. The 2024 work approached the problem differently. Instead of treating the warp effect as a free-floating distortion, the researchers constructed a model involving a stable shell of matter surrounding the warp region. Inside that shell is the spacecraft. Around it is the engineered space-time geometry. The shell provides a physical source for the geometry, and mathematically, it can be assigned positive ADM mass. This is a crucial detail. The 2024 paper reports that the model combines a stable matter shell with a shift vector distribution resembling well-known warp drive solutions, including the Alcubierre metric. The authors numerically generated the spacetime metric and evaluated the relevant energy conditions. Suddenly, the warp bubble began to look less like a magical region of distorted space, and more like a physical gravitational configuration. That distinction matters enormously. A warp drive cannot simply be declared into existence by writing down a metric. General relativity demands a source. Energy and momentum shape spacetime, so the question becomes, what kind of matter distribution produces the desired geometry? The 2024 model provided one possible answer: a matter shell, a carefully chosen distribution, and a space-time geometry that, within the model, satisfies the energy conditions. But there is a crucial word hiding in the title: constant velocity, and another, subluminal. The bubble remains below the speed of light. That means this was not an FTL engine. It did not solve the ultimate problem, but it attacked one of the problems that had made warp drive physics look physically absurd: the requirement for exotic negative energy. This is where the story becomes subtle. It would be easy to look at the 2024 research and say, scientists have proved warp drive is possible. That statement would be misleading. What they demonstrated was much narrower. They found a particular mathematical space-time configuration in general relativity that is subluminal and, within their analysis, satisfies the standard energy conditions by using a regular matter shell with positive ADM mass. That is a theoretical result. There is still no physical warp bubble in a laboratory. No spacecraft has been placed inside one. No macroscopic space-time distortion has been generated on demand. And no experiment has shown that such a shell can actually be assembled from real materials. But the distinction between those statements is exactly what makes this field scientifically interesting. The question has evolved. It is no longer simply, does the mathematics permit a warp bubble? Now researchers can ask, what matter distribution would physically support one? And then, can that distribution be made stable? And eventually, can it be controlled? Those are engineering questions. But they begin with physics. One of the tools that helped make this exploration possible is called warp factory. It sounds almost like something from science fiction. But the underlying idea is straightforward. Warp factory is a numerical toolkit developed by researchers at Applied Physics for analyzing warp drive spacetimes. Instead of forcing every calculation into a simple analytical formula, researchers can use numerical methods to explore a much larger range of possible geometries. The toolkit can evaluate Einstein's field equations. It can calculate energy conditions. It can determine metric scalars. And it can visualize the resulting space-time and stress-energy distributions in 2 and 3 dimensions. That may sound like a technical improvement. It is actually a major change in the way researchers can search. Imagine trying to explore an enormous mountain range using only a pencil and a paper map. You can calculate the height of a few mountains. You can draw several routes. But most of the landscape remains unexplored. Now imagine having a high-resolution digital terrain model. You can alter the parameters, change the shape, search for valleys, measure gradients, optimize routes. Warp Factory does something conceptually similar for mathematical space-time geometries. It allows researchers to explore possibilities that are too complicated to handle conveniently by hand. The important word is possibilities. It does not simulate a real engine sitting in a laboratory. It explores solutions to Einstein's equations. That distinction must remain clear. Then came another development. In late 2025, physicist José Rodal published a new warp drive construction with a different strategy for reducing negative energy requirements. His model was described as a continuous, analytically derived warp drive space-time with an irrotational shift vector flow. The reported results were striking. At matched parameters, the model reduced the peak proper energy deficit by roughly a factor of 38 compared with the Alcubierre model, and by roughly 600 compared with the Notario model examined in the paper. The peak NEC violation was also reported to be more than 60 times smaller than Notario's under the comparison used. Those numbers sound spectacular, but they need context. A reduction in the amount of negative energy required is not the same as eliminating the need for negative energy. Rodal's model still contains negative energy contributions. The paper itself reports a non-zero negative energy component and analyzes the remaining energy condition violations. So the lesson is not, negative energy has been eliminated. The lesson is, the geometry of a warp drive can be redesigned in ways that dramatically change how severe the negative energy problem becomes. That is a much more scientifically defensible and arguably more interesting result, because it suggests that the original Alcubierre bubble may have been only one point in a much larger mathematical landscape. Change the geometry, and the energy requirements change with it. Change the velocity profile, and the stress-energy distribution changes. Change the symmetry, and entirely different physical properties can emerge. The search becomes an optimization problem. Instead of asking for one perfect warp bubble, physicists can search through thousands, or potentially millions, of possible space-time configurations. Then came 2026. And this time, the problem was not simply energy. It was motion itself. A useful spacecraft cannot merely exist at a constant velocity. It must accelerate. It must slow down. It must steer. It must change direction. It must eventually stop. A theoretical warp bubble that can cruise at a fixed velocity is not enough. A real spacecraft needs control. In June 2026, physicist Ann T. Le proposed a new model in a preprint titled "Steering a Warp Drive Without Exotic Matter." The paper addresses exactly this problem. It describes a compact, positive energy configuration driven through photon rocket recoil, with a flat passenger cavity and a matter shell surrounding it. The key idea is remarkably different from the popular image of a magical bubble accelerating itself through space. Instead, the proposed configuration behaves as a reaction drive. Momentum is carried away through radiation. The system changes its motion by paying an energy cost. And the paper derives a relationship between acceleration and Bondi mass loss, the gravitational equivalent of keeping track of the system's energy budget as it radiates. In other words, the warp drive does not get something for nothing. If it accelerates, it pays. If it steers, it pays. If it radiates momentum away, its available mass energy decreases. That may sound less exotic than a Star Trek engine. Scientifically, it is much more interesting, because it begins treating warp propulsion as a genuine problem in relativistic energy and momentum accounting. But once again, there is a critical limitation. The 2026 model is explicitly described by its author as causal and subluminal. It does not provide faster-than-light travel. That distinction is essential: a positive energy warp drive that can accelerate is not the same thing as a positive energy FTL warp drive. A spacecraft traveling below light speed, even if it uses a bizarrely curved space-time geometry, is still inside the relativistic speed limit. The ultimate question remains unanswered. Can a physically acceptable warp geometry ever become superluminal? That is where the story becomes much harder, because once the bubble crosses the light speed threshold, new problems emerge. Causality, horizons, information, reference frames, and potentially the relationship between faster-than-light, motion, and travel into the past. So the 2024, 2025, and 2026 developments should not be presented as 3 steps toward a machine that is almost ready. They are 3 steps toward something more fundamental: a better understanding of what warp spacetime can and cannot do. Think about what has happened since Alcubierre's original proposal. In 1994, the warp drive appeared to require exotic negative energy. In 2021, researchers developed broader frameworks for physical warp drives, including positive energy subluminal configurations. In 2024, a constant velocity model was presented that satisfies the energy conditions using a stable matter shell with positive ADM mass. In 2025, new geometries attempted to reduce negative energy requirements substantially, even though they did not eliminate them. And in 2026, a new preprint explored how a positive energy warp configuration might actually steer and accelerate while remaining explicitly causal and subluminal. The progression is striking. The warp drive is slowly being pulled apart into separate scientific questions. Can the geometry exist? Can it satisfy energy conditions? Can it have positive energy? Can it be stable? Can it accelerate? Can it steer? Can it stop? And finally, can it ever go faster than light? That final question remains open, and perhaps that is exactly how a serious scientific field should progress. Not by announcing that science fiction has suddenly become reality, but by taking one impossible-looking problem and breaking it into smaller problems that mathematics can actually test. The warp drive of 2026 is not a spaceship. It is not a machine. It is not an FTL portal. It is a collection of increasingly sophisticated space-time models. But something has undeniably changed. We are no longer asking only whether a warp bubble can be written on paper. We are learning how to construct, analyze, optimize, accelerate, and steer theoretical warp geometries using increasingly physical assumptions. The distance between mathematics and engineering is still enormous. The distance between subluminal warp and faster-than-light travel may be even larger. But the frontier has moved, and that creates the central mystery of our journey. If physicists can gradually remove one impossible requirement after another, what happens when they finally ask the universe to cross the last boundary? The boundary that Einstein's theory has protected for more than a century. The speed of light. Because making a warp drive more physical is one problem. Making it faster than light is another entirely. There is a moment in every warp drive discussion when the excitement has to stop. The equations are beautiful. The space-time geometry is fascinating. Positive energy models have begun to appear. Some researchers have even explored how theoretical warp configurations might accelerate or steer. And then comes the question that cannot be avoided. Can any of this actually go faster than light? Not almost as fast. Not 99% of the speed of light. Not a clever way of crossing an enormous distance while remaining below the relativistic limit. We mean something much more extreme. A genuine faster-than-light, or FTL, warp drive. This is where the story becomes considerably more difficult, because the phrase warp drive covers several very different possibilities. A subluminal warp drive travels below the speed of light. A luminal configuration would approach or reach the light speed boundary. A superluminal warp drive would produce effective motion faster than light. Those three regimes should never be treated as interchangeable, and this distinction changes everything. The recent positive energy warp drive models are important precisely because some of them demonstrate physically interesting subluminal configurations. But a subluminal warp drive does not break Einstein's speed limit. It does not prove FTL travel. It does not allow information to cross the galaxy instantaneously, and it does not solve the deepest problem. The real frontier begins only when the warp bubble becomes superluminal. That is where space-time itself starts behaving in ways that challenge our understanding of cause and effect. To see why, imagine two spacecraft. One leaves Earth. The other remains behind. The traveling spacecraft sends a signal back. At ordinary speeds, there is no mystery. Event A happens first. The spacecraft sends the signal. Event B happens later. The receiver gets it. The sequence is unambiguous. But special relativity tells us that space and time are not absolute. Different observers moving relative to one another can disagree about the time and position of distant events. Normally, This does not create contradictions. The structure of space-time preserves causality. Light cones define which events can influence which others. An event inside your future light cone can be affected by you. An event outside it cannot receive an ordinary causal signal from you. That structure is one of the deepest organizing principles of relativity. Now, imagine that you could send a signal faster than light. The signal would move outside the ordinary light cone. It would travel through a space-like interval. And something strange happens. Another observer, moving relative to you, could describe the same two events with a different ordering in time. From your perspective, you send the message first, then they receive it. But in another inertial frame, the reception event could occur before the transmission event. That sounds impossible. But it is a direct consequence of Lorentz transformations for space-like separated events. And this is where FTL becomes much more than a question about speed. It becomes a question about causality. Imagine you are standing on Earth in the year 2100. You possess a hypothetical FTL communication device. You send a message to a spacecraft traveling rapidly away from Earth. The message crosses the distance faster than light. The spacecraft receives it. Now imagine the spacecraft is moving relative to Earth. It sends an FTL reply. Because the spacecraft and Earth are moving relative to one another, the return signal can be arranged under the standard relativistic argument, so that Earth receives the reply before the original message was sent. The result is a closed causal loop. You could receive an answer to a question before you asked it. And that creates a devastating paradox. Suppose the reply says, "Do not send the first message." If you obey the instruction, why did you ever receive the warning? And if you never send the original message, what caused the warning to arrive? The problem is not merely philosophical. It arises because faster-than-light signaling and relativity allow different observers to disagree about the temporal ordering of space-like separated events. With suitable arrangements, that disagreement can be turned into a causal loop. Modern analyses of warp drive spacetimes have explicitly examined this connection between superluminal warp travel and closed time-like curves. One 2023 study constructed a mathematical scenario in general relativity where two appropriately arranged warp drives could form a closed time-like geodesic, allowing a path back to the traveler's own past. This is the deeper problem. FTL is not simply faster transportation. It can become a potential machine for manipulating the order of cause and effect. And this brings us back to the warp bubble. At subluminal speeds, the theoretical picture is already difficult. At superluminal speeds, new structures appear. Theoretical studies of warp spacetimes identify horizons in the superluminal regime. These horizons can create a peculiar problem. The occupants of a warp bubble may not be able to communicate freely with all regions of the bubble's exterior. In some formulations, an observer inside the spacecraft cannot simply create or control the bubble on demand using ordinary signals, because the bubble's own causal structure prevents information from reaching the required regions. That is a remarkable consequence. The faster the bubble becomes, the less control the crew may have over the very geometry carrying them. Imagine accelerating into a vehicle whose steering controls cannot communicate with the front of the vehicle. You may have a beautiful engine, but you cannot necessarily tell it where to go. This is one reason why a superluminal warp drive is not merely an upgraded version of a subluminal one. Crossing the light speed boundary can change the causal structure of the entire space-time. There is another issue. The energy condition problem does not simply disappear when we make the bubble faster. In fact, the superluminal case can become even more difficult. Several analyses have argued that generic, physically reasonable warp drives in standard general relativity violate the null energy condition and therefore face broader energy condition problems. This matters because recent positive energy results must be interpreted carefully. A positive energy, subluminal solution is a significant theoretical development, but it does not automatically extend to the superluminal regime. The mathematical conditions that make one geometry acceptable do not guarantee that another geometry, moving faster than light, will behave the same way. Changing the velocity can change the entire stress-energy structure. The bubble may require different pressures, different energy densities, different matter distributions, different boundary conditions, and perhaps entirely different physics. This is why the phrase, "Scientists have solved the negative energy problem," would be dangerously misleading. Some specific subluminal models have been constructed with positive energy matter. That is very different from proving that a stable, controllable, superluminal warp drive can be built without exotic energy. The FTL problem remains. Now consider Einstein's original speed limit. It is often summarized in one sentence: nothing can travel faster than light. That statement is useful, but it is incomplete. Einstein's special relativity specifically tells us that a massive object cannot be accelerated through the local speed of light. The limit applies to local motion through space-time. That is why the warp drive concept was interesting in the first place. A warp bubble attempts to avoid making the spacecraft locally outrun a nearby photon. The ship remains within its local space-time environment. The global geometry changes. This distinction means a warp drive does not necessarily violate the most basic local statement of special relativity simply by changing the geometry of space-time. But that does not mean global FTL is automatically safe. And this is the subtle point that often gets lost. Local relativity can remain intact while the global space-time geometry creates deeper causal problems. Think of a road. There may be a local speed limit everywhere along the road. No car is allowed to exceed it locally. But if you somehow reshape the entire road so that two distant locations become connected by a shortcut, the total journey can become faster than an ordinary light signal traveling through the original geometry. The local rules have not necessarily been broken. The global structure has changed. In general relativity, global causal structure matters enormously. Space-time is not simply a collection of isolated local speed limits. Its topology and geometry determine which events can influence which others. That is why the FTL question cannot be answered simply by saying, Einstein says no. The more precise question is, can general relativity contain a physically realizable, superluminal space-time geometry without creating contradictions with causality, energy conditions, and quantum physics? We do not yet have a definitive answer. And this leads us to one of the most famous ideas in theoretical physics, Hawking's chronology protection conjecture. In 1992, Stephen Hawking proposed that the laws of physics may somehow prevent the formation of closed time-like curves. and therefore prevent macroscopic time machines from appearing in the real universe. The idea was not that someone had discovered a simple equation saying, "Time travel forbidden." It was much more subtle. Hawking suggested that quantum effects could become extremely important as a space-time approaches the formation of a chronology horizon. Quantum fields might generate enormous vacuum polarization effects. The resulting stress energy could become large enough to alter the space-time itself. In other words, nature might destroy the time machine before the time machine can fully exist. This is the idea of chronology protection. It is a fascinating possibility, but it remains a conjecture. We do not possess a complete theory of quantum gravity capable of definitively settling the issue. There have also been theoretical studies that challenge or complicate simple versions of chronology protection. So we should not say that Hawking proved time travel is impossible. He did not. He proposed a profound physical conjecture about why the universe might protect causality, and that uncertainty is exactly where warp drive research becomes interesting. Suppose for a moment that future physicists discover a genuine superluminal metric. It satisfies the Einstein equations. It requires no impossible negative energy source. It remains stable. It can be generated by physical matter. And somehow, it can be controlled. Would that automatically mean FTL travel is possible? Not necessarily. We would still need to determine whether the geometry can exist globally without producing pathological causal structures. Can the bubble be created? Can it be accelerated? Can it be stopped? Can the crew control it from inside? Can information enter and leave the bubble? Can the bubble interact safely with ordinary matter? Can two bubbles coexist? Can a bubble be combined with another relativistically moving system? And most importantly, does the resulting space-time permit closed time-like curves? These are not details for a future engineer. They are fundamental tests of whether the proposed geometry belongs to the physical universe at all. There is another reason for caution. A mathematical solution to Einstein's equations can be perfectly valid and still fail to describe something nature actually allows. General relativity has many exotic solutions. Some contain unusual causal structures. Some require matter with strange properties. Some are unstable. Some may depend on idealized boundary conditions that cannot be realized physically. The existence of a solution proves that the equations permit a mathematical space-time. It does not prove that the universe can construct that space-time. This distinction is essential. The same applies to warp drives. A metric can be elegant. Its curvature can be calculated. Its energy density can be plotted. Its trajectory can be simulated. But nature still has the final vote. And so far, nature has not demonstrated an FTL warp bubble. This is why the recent advances are both exciting and sobering. Researchers have made progress in constructing more physically motivated warp geometries. They have explored positive energy matter. They have investigated constant velocity configurations. They have developed numerical tools for studying stress energy distributions. They have even begun examining theoretical ways to accelerate or steer subluminal warp configurations. But none of that means the light barrier has been broken. The barrier is still there, and it may be deeper than a simple speed limit. It may be a protection built into the causal structure of space-time itself. Perhaps the universe allows us to bend space. Perhaps it allows us to compress distances. Perhaps it allows a spacecraft to travel through a curved geometry without experiencing enormous local acceleration. But perhaps when we try to push that geometry beyond the speed of light, something fundamental intervenes. Energy conditions, quantum fields, horizons, causality, or a theory of quantum gravity that we have not discovered yet. We simply do not know. And that uncertainty is important, because the honest scientific position is not. FTL warp drive has been proven impossible. Nor is it. FTL warp drive has now been proven possible. The evidence supports neither extreme. The correct statement is more fascinating. We know how to write down superluminal space-time geometries. We know that they can be studied mathematically. We know they raise deep causal problems. We know many warp constructions encounter severe energy condition difficulties. And we know that the recent positive energy advances have, so far, primarily concerned subliminal configurations rather than a demonstrated FTL engine. The light barrier has not been broken. But we have learned something perhaps more valuable. We have learned exactly where the real barrier is. It is not simply the number 299,792 kilometers per second. The deeper barrier is the architecture of space-time itself. If humanity ever crosses it, we will not merely have built a faster spacecraft. We will have discovered that the universe permits us to manipulate its causal structure in ways we do not yet understand. And that raises the ultimate question. If the mathematics allows a superluminal warp geometry, what would it take to make that geometry physically real? Because before humanity can build a faster-than-light engine, we first have to determine whether the universe will let us build one at all. There is a moment when every beautiful scientific idea has to face the same question. Not. Can we write the equation? Not. Can we simulate it? Not even. Does general relativity permit the geometry? The real question is much harder. Can we build it? This is where the dream of the warp drive encounters its greatest obstacle. Because a mathematical space-time metric is not an engine. A computer simulation is not a spacecraft, and a solution to Einstein's equations is not automatically a machine that can be assembled inside a laboratory. The distance between those three things may be enormous. Imagine that tomorrow, physicists discover a perfect mathematical description of a warp bubble. The geometry is stable. The energy conditions are satisfied. The equations contain no obvious contradiction. The bubble can, in principle, carry a spacecraft. It would be one of the greatest theoretical breakthroughs in human history. And yet, the spacecraft would still be sitting on Earth. Nothing would have moved. Because the next problem is engineering, and engineering begins with energy. To create a warp bubble, we need to create a particular distribution of stress and energy. In general relativity, gravity is not something that can simply be switched on with a conventional motor. The curvature of space-time is produced by the stress-energy distribution of the system. That means a practical warp drive would need to manipulate enormous amounts of energy, momentum, pressure, and stress in extraordinarily precise ways. This is fundamentally different from generating electricity. We already know how to move electrons. We know how to produce electromagnetic fields. We know how to accelerate charged particles. But gravity is different. The gravitational effect produced by ordinary human technology is incredibly weak. The mass of a spacecraft creates gravity, but it is nowhere near enough to generate the kind of engineered space-time curvature envisioned by warp drive metrics. To make the geometry significant on macroscopic scales, the required energy budget can become enormous. And there is an important distinction here. The fact that a particular theoretical model has a finite energy requirement does not mean that the requirement is technologically achievable. A calculation can tell us, this configuration requires a certain amount of energy. Engineering then asks, where does that energy come from? How do we generate it? How do we store it? How do we deliver it? How do we prevent it from destroying the spacecraft? And how do we control it with sufficient precision? These questions have no known technological answers. Now imagine the warp bubble itself. It is not simply an invisible sphere. In many theoretical descriptions, the bubble has a region where the space-time geometry changes rapidly. That transition can be thought of as a kind of shell or boundary. In some newer models, this shell contains matter. That matter is not merely decoration. It is part of the physical source responsible for the geometry. And this creates another problem. The shell has to remain stable. Imagine building an enormous structure around a spacecraft in which every part of the structure contributes to the curvature of space-time. If the distribution is slightly wrong, the geometry changes. If the energy density fluctuates, the geometry changes. If the shell becomes unstable, the warp configuration could collapse or evolve into something completely different. We have no known material that has been demonstrated to behave as the matter shell required by these theoretical models under the relevant conditions. We have no laboratory technique capable of arranging macroscopic matter into the precise stress-energy distribution demanded by a warp metric. And we do not know whether such a configuration could remain stable while moving through interstellar space. That is a problem of an entirely different magnitude. Then comes the question that seems almost embarrassingly simple. How do you turn it on? With a conventional spacecraft, the answer is easy. You ignite the engines, fuel reacts, thrust is produced, the spacecraft accelerates. A warp drive does not have such a straightforward operating sequence. The bubble itself is a space-time configuration. To create it, you would have to establish the required energy and momentum distribution around the spacecraft. But before the bubble exists, there is no bubble to carry the spacecraft. So how does the transition occur? Does the spacecraft generate the geometry from inside? Does an external system create the bubble? Does the bubble form gradually? Does it appear suddenly? Can the bubble be created safely around an occupied spacecraft? These are not merely practical engineering questions. They are questions about the dynamics of spacetime. A static solution tells us what the geometry looks like once it exists. It does not necessarily tell us how nature evolves from ordinary flat spacetime into that configuration. This distinction is critical. A blueprint showing what a bridge looks like when finished does not explain how the bridge was constructed while traffic was moving beneath it. Likewise, a warp metric describing a completed bubble does not automatically provide a physical mechanism for creating the bubble. And then there is acceleration. A real spacecraft cannot remain at one velocity forever. It has to leave Earth. It has to accelerate. It has to reach cruise conditions. Eventually, it must slow down. If the destination is another star, the spacecraft must perform this sequence in reverse. This is where the 2026 theoretical work on steering and acceleration becomes especially interesting. Researchers have begun exploring positive energy configurations that can change velocity while remaining subliminal. But even these models reveal the enormous cost of propulsion. Momentum must be conserved. Energy must be conserved. If the system changes its velocity, something else must carry away or provide the corresponding momentum. In the 2026 photon rocket-based model, radiation provides the necessary recoil mechanism. The system, therefore, pays for acceleration through energy and mass loss. Arcsieve. There is no free propulsion. Even a warp geometry cannot simply accelerate without accounting for momentum. This is important because popular images of warp drives often show a bubble accelerating, as if space-time itself were doing all the work for free. Physics does not grant such a shortcut. A practical system must obey conservation laws. Steering creates another challenge. Imagine a spacecraft traveling toward a distant star. The bubble is perfectly symmetrical. Then the pilot wants to turn left. What does turn left mean for a space-time geometry? The entire warp structure has to change. The stress-energy distribution has to change. The curvature changes. The direction of the bubble changes. And all of this must happen without destabilizing the spacecraft's local environment. A conventional spacecraft turns by producing a force. Thrusters change its momentum. A warp drive would potentially need to reshape the geometry of the spacetime carrying the spacecraft. That is a fundamentally different control problem. It would be closer to steering the geometry of a gravitational field than steering an airplane. And we have never done anything remotely comparable. Then comes the interstellar environment. Space looks empty. It is not. Between the stars are extremely thin populations of gas, dust, plasma, cosmic rays, and high-energy particles. At ordinary spacecraft speeds, these particles can already create significant hazards. At relativistic speeds, the problem becomes much more severe. A tiny grain of dust can carry enormous kinetic energy when encountered at a substantial fraction of light speed. A particle that would be harmless to a slow spacecraft can become a high-energy projectile. Now imagine a warp configuration traveling through interstellar space. How does the bubble interact with those particles? Do particles accumulate around the bubble? Are they accelerated by the changing geometry? Are they trapped? Do they collide with the spacecraft when the bubble collapses? Could high-energy radiation be concentrated near the front of the bubble? These questions are not fully resolved. They depend strongly on the specific warp geometry. But they illustrate a broader principle. Even if we solved the mathematics of the bubble itself, the universe outside the bubble would still have to be dealt with. And then we encounter one of the most disturbing problems. What happens when the bubble stops? Suppose a warp spacecraft travels from Earth to another star. The journey is complete. The bubble decelerates. The spacetime geometry returns toward its ordinary configuration. But what happens to the energy and radiation accumulated during the journey? What happens to matter that interacted with the bubble? What happens to fields that were distorted? Could energy be released when the bubble collapses? Could particles be concentrated in dangerous ways? Could the transition itself produce an enormous burst? These questions remain dependent on the detailed geometry, but they highlight something often ignored. Starting a warp bubble is not the only problem. Ending the warp bubble is a problem too. The situation becomes even more difficult for superluminal configurations. As we explored in the previous chapter, FTL warp geometries can contain horizons and complicated causal structures. A bubble moving faster than light may create regions that cannot communicate normally with one another. This produces a troubling engineering paradox. How can the crew control the front of a bubble if information cannot reach the front from inside? How do you tell the bubble where to go? How do you stop it? How do you correct its trajectory? How do you prevent it from entering an unwanted region of space? A faster-than-light spacecraft could theoretically become a vehicle whose own causal structure limits its ability to control itself. That is not merely an engineering inconvenience. It may indicate a deeper physical restriction. There is also the problem of back reaction. General relativity tells us that matter and energy shape spacetime. But once spacetime is strongly curved, the behavior of matter and fields can change. Those changes can, in turn, alter the geometry. This feedback is called back reaction. A theoretical calculation may assume an idealized stress-energy distribution, but in a real physical system, the geometry itself interacts with quantum fields, radiation, particles, and the matter producing the curvature. The system is not a frozen mathematical picture. It is dynamic. And dynamic systems can become unstable. A tiny perturbation can grow. A stable configuration can become unstable under motion. Quantum effects can become important. Energy can be redistributed. The bubble may change shape. This is one reason why a static metric is only the beginning. A practical warp drive would need to remain stable under perturbations. It would need to survive its own motion. It would need to interact with the environment. And it would need to maintain the required geometry while carrying a spacecraft full of people. We currently have no experimental evidence that such a configuration can do any of these things. Then there is heat. Every real machine produces waste heat. Nuclear reactors produce heat. Lasers produce heat. Particle accelerators produce heat. Power electronics produce heat. Even spacecraft operating in deep space must manage thermal energy. A hypothetical warp system involving enormous energy flows would face an extraordinary thermal management problem. Where does the waste energy go? How is it radiated? What happens to the spacecraft's structure? Can the system operate continuously? Can the required energy be supplied without vaporizing the surrounding equipment? These questions sound mundane compared with curved spacetime, but engineering history is full of technologies defeated not by their central principle, but by secondary problems. Heat, vibration, materials, stability, control, manufacturing. A warp drive could face all of them at once. And perhaps the biggest problem is the simplest. We do not have the materials. No material currently known has been demonstrated to withstand the hypothetical conditions associated with a macroscopic warp configuration. We have no known structure capable of generating and maintaining the required stress-energy distribution. We have no laboratory device that creates a controlled warp bubble. No experiment has transported matter inside a warp bubble. No spacecraft has been accelerated by engineered spacetime curvature. Not even a tiny unmanned probe. This is why claims that humanity is close to building a warp drive should be treated with extreme caution. The recent theoretical advances are genuine. They are interesting. They deserve serious study. But they are not prototypes. They are not engines. They are mathematical models. The difference matters. And yet, something important has changed. The research frontier is becoming more precise. Instead of asking, "Can we build Star Trek?" physicists can ask, "Can a warp geometry satisfy the energy conditions? Can it be supported by positive energy matter? Can it remain stable? Can it accelerate? Can it steer? Can it interact safely with ordinary matter? Can its causal structure remain consistent? Can quantum effects destabilize it? Can the required energy be generated? Can the geometry actually be created from an initially ordinary space-time?" Each question eliminates another layer of fantasy. Each answer brings us closer to understanding what nature truly permits. And perhaps that is what makes the Warp Drive story scientifically valuable. We do not yet know how to build one. We do not even know whether a practical one is possible. But we are beginning to understand exactly what would have to be solved. The dream is becoming a checklist: energy, matter, stability, control, acceleration, steering, radiation, back reaction, causality, and finally, FTL. The last item may be the hardest of all. Because solving every engineering problem below the speed of light would still leave one fundamental question unanswered. Can space-time itself be engineered to carry a physical object beyond the light cone? If the answer is yes, humanity would have discovered a new form of transportation. But if the answer is no, the warp drive research of our era may still teach us something extraordinary about the architecture of the universe. Either way, the next breakthrough will not come from simply making a bigger rocket. It will come from understanding space-time itself. And perhaps, somewhere inside that understanding, is the key to the final barrier. There is one question that has followed us from the beginning. A question that sounds simple, but may represent one of the deepest challenges in modern physics. Can humanity ever travel faster than light? After everything we have explored, the most honest answer is still, we do not know. There is currently no experimental evidence that a physical spacecraft can achieve faster than light propulsion. No warp engine has been built. No laboratory has produced a macroscopic warp bubble capable of transporting matter. No spacecraft has crossed the light barrier, and no existing experiment has demonstrated that the universe permits controllable FTL travel. The dream remains theoretical, but something has changed. And that change is worth understanding. Because the story of the warp drive is no longer simply a story about science fiction. It is a story about what Einstein's equations actually allow. In 1994, Miguel Alcubierre showed that general relativity could describe an extraordinary space-time geometry. A spacecraft could theoretically sit inside a region of relatively calm space-time, while the geometry around it contracted and expanded. The ship would not locally outrun a beam of light. Instead, space-time itself would be manipulated. That idea was revolutionary, but it came with an enormous price. The original geometry required exotic energy conditions that appeared far beyond anything humanity could produce. For decades, that seemed to be the end of the story. Then researchers began exploring alternatives. In 2021, Alexei Bobrik and Gianni Martire developed a broader framework for physical warp drives and presented examples of positive energy, subluminal configurations, ARCSIV. In 2024, Jared Fuchs and colleagues published a constant velocity physical warp drive solution using a stable matter shell and positive ADM mass while satisfying the standard energy conditions within their model, ARCSIV. In 2025, other researchers continued exploring alternative geometries that reduce the severity of negative energy requirements. And in 2026, theoretical work proposed a positive energy configuration capable of steering and accelerating while remaining causal and subluminal, ARCSIV. None of these developments produced an FTL spacecraft, but they changed the conversation. The question became less about whether warp geometry could exist on paper, and more about what physical resources would be required to create and control it. That is a profound change, because scientific progress often begins when an impossible question is replaced by a difficult one. For decades, the question was, does warp drive violate physics? Today, that question is too simple. A better question is, what kinds of warp geometry are compatible with known physics? And then, can we create them? Then, can we control them? Then, can we power them? Then, can we accelerate them? And finally, can any physically realizable configuration become superluminal? Each question is harder than the last, and each one separates mathematics from engineering a little more clearly. This distinction is essential. A mathematical solution tells us that the equations can describe a particular space-time. A physical experiment tells us that nature can actually produce the required conditions. A propulsion system requires us to generate those conditions reliably. An interstellar spacecraft requires that system to operate safely for long periods. And an FTL spacecraft would require something beyond all of that. A superluminal geometry that remains physically consistent. That final step has not been achieved. So imagine a future laboratory, not a secret military facility, not science fiction spaceship. A real scientific laboratory built perhaps decades or centuries from now. Inside is a machine unlike anything humanity has ever constructed. At its center sits a small spacecraft. Around it is an enormous apparatus designed to manipulate the distribution of energy and momentum. The experiment begins. The gravitational field changes. Space-time begins to curve. Sensors detect a tiny deformation. For the first time in human history, engineers have deliberately altered space-time geometry in a controlled environment. That would already be revolutionary. It would not mean FTL. It would not even mean interstellar travel. But it would represent a fundamental transition. Humanity would have moved from observing curved space-time to engineering curved space-time. That distinction could define the beginning of a completely new technological era, the warp age. If that era ever arrives, the first practical warp applications may not involve faster-than-light travel at all. They could begin with subliminal propulsion. A spacecraft might use engineered space-time to reduce the acceleration felt by its crew. It might optimize long-distance travel. It might provide new methods of transporting massive objects. It might reveal ways of manipulating gravitational fields that are currently beyond our capabilities. The first warp technology may therefore look nothing like the fictional warp drive. It may be slower, smaller, more limited, but scientifically, it could be the beginning. Because technology rarely appears in its final form, the first airplane did not resemble a modern passenger jet. The first computers did not resemble smartphones. The first rockets did not resemble reusable launch vehicles. A future warp technology might begin as a laboratory experiment so weak that the effect is almost invisible. Then the scale could grow: microscopic, laboratory, orbital, planetary, interplanetary, and perhaps, eventually, interstellar. Now imagine that the final barrier is eventually crossed. Imagine a spacecraft leaves Earth. The engines do not roar. There is no gigantic explosion. Instead, the space around the vehicle begins to deform. The distance between Earth and Alpha Centauri changes. The stars shift. The bubble forms. And the spacecraft disappears from the solar system's immediate neighborhood. For the crew, the journey could be measured in hours, perhaps minutes. The nearest star would no longer be an astronomical abstraction. It would become a destination. Alpha Centauri would become a place we could visit. That would change humanity forever. The stars would stop being points of light. They would become locations, destinations, potential homes, scientific laboratories, and perhaps the first stepping stones toward an interstellar civilization. But such technology would also create questions that physics alone cannot answer. Who controls it? Who gets to use it? What happens when distances that once protected civilizations disappear? How does humanity prevent conflict when military forces can cross planetary distances almost instantly? What happens to borders, to economies, to resources, to political power? And perhaps the most profound question: what happens to our understanding of ourselves when the stars become reachable? For thousands of years, humanity lived under a simple cosmic assumption. The universe was vast. We were small. The stars were distant, and physical distance protected us from them. FTL travel would destroy that assumption. The galaxy would become smaller, not physically, but culturally, politically, economically, psychologically. The Milky Way could become a connected environment. And humanity would have to decide what kind of civilization it wanted to become within it. But there is another possibility. Perhaps FTL will never work. Perhaps every attempt to construct a superluminal warp geometry will eventually encounter the same obstacles: energy conditions, quantum instability, causal paradoxes, horizons, back reaction, or some deeper principle of physics that we have not yet discovered. Perhaps nature allows us to bend space-time, but never enough to cross the light cone. If that happens, the warp drive dream would still have been valuable, because the attempt to understand warp propulsion would have forced physicists to investigate the deepest relationship between matter, energy, gravity, quantum mechanics, and space-time. Sometimes a failed technological dream produces a scientific revolution. The attempt to build a machine can reveal that our understanding of the universe was incomplete, and that may ultimately be the greatest legacy of the warp drive. Not the spacecraft, not the journey to another star, but the knowledge gained while trying to understand why such a journey may or may not be possible. Today, we are still at the beginning. We have equations. We have simulations. We have theoretical models. We have increasingly sophisticated mathematical tools. We have proposed positive energy subliminal warp geometries. We have explored ways of reducing energy condition violations. We have begun studying acceleration and steering. But we do not yet have the machine. The distance between mathematical solution and physical experiment remains enormous. The distance between physical experiment and propulsion system is larger still. And the distance between a practical propulsion system and interstellar FTL may be the greatest leap of all. So, perhaps the most honest image of humanity's future is not a starship already waiting on a launch pad. It is a laboratory, a scientist staring at a computer screen, a space-time equation slowly changing, a simulation revealing a geometry that nobody has seen before, and somewhere in those equations, perhaps a clue telling us whether the universe is a prison with an absolute speed limit, or a structure whose geometry can eventually be shaped. For more than a century, Einstein's theories have taught us that space and time are not passive backgrounds. They are physical. They bend, they expand, they contract. They carry gravitational waves across the cosmos. They determine how clocks run. They determine how light travels. And perhaps, one day, they may become something humanity can engineer. That is the deepest idea behind the warp drive. Not simply traveling faster, not simply building a better rocket, but learning to manipulate the fabric through which every journey takes place. The greatest limitation may never have been the engine. It may never have been the fuel. It may never have been the spacecraft. Perhaps the true limitation has always been our understanding of space-time itself. And if humanity eventually learns to control that geometry, the universe may suddenly become very different. The distance to the stars would change. The meaning of a journey would change. And the boundary between our world and the rest of the galaxy would begin to disappear. But tonight, we are still standing on Earth. The stars remain distant. The speed of light remains undefeated. The warp bubble remains a mathematical possibility, not a working machine. And perhaps that is exactly where the next great scientific revolution begins. Not with certainty, but with a question. What if the universe has been telling us all along that we were asking the wrong question? Maybe the question was never, how do we make a spacecraft travel faster than light? Maybe it is, how do we change the space that separates us from where we want to go? And if humanity ever finds that answer, we may discover that the greatest barrier was never the speed of the ship. It was our ability to bend the geometry of the universe itself. And somewhere, beyond the last equation we currently understand, the first chapter of the warp age may already be waiting.